Yeah, so in the last class, we started looking into neural networks, right? And we were looking at different sources of error that can occur because of the use of a neural network or any function class, right? So by limiting to a certain class of functions, you may not be able to exactly get the underlying distribution, right? And in case of supervised learning, that would be the distribution of y given x, right? So it cannot always recover it exactly, so you have several sources of error. So to recall, right, there is this like oracle, that's the underlying function you want to approximate, right? So call this h oracle, I guess, of x, right? So this is the true underlying function, right? So of course this, you could think of y as being a deterministic function of x through this oracle, or it could be noisy, right? So in the case when this is probability of y given x, that means there's also randomness in terms of how y is generated. Both scenarios are okay, for most of this lecture. It doesn't matter whether y is randomly generated or a deterministic function. But at some point there's slight change, and I will point that out. So for now it could be either case, right? But the idea is there's an underlying function, which is the oracle function in terms of x, and y is this, right, oracle function plus noise. And since we cannot fit this exactly in general, I mean, if I gave the example of how we have the classifier in our brains, right? Classifier or a visual perceptron on how we perceive images, and that cannot be exactly fitted into any finite sized neural network, maybe most likely not, right? At least not with the technology we have today. So instead of that, we would do this on some finite complexity class, right? Like a finite sized neural network. And so we would get the best approximation, right? So this is now like the notation I'll use H star. This is the, right, there's an approximation error in fitting this oracle function. And then we said there's further error because this is if I had infinite number of samples. If I have only finite number of samples, I can only do the empirical risk minimization, right? So I can minimize some empirical risk, right? So based on my finite data set, and that incurs estimation error. And also, if the optimization when it's non-convex may not be globally optimal, there's also algorithmic error or optimization error. And that's what you finally get at the end, right? So the idea was to try to break down the deviation from what is the true underlying oracle function and what we estimate into multiple parts. And so primarily it's approximation and estimation error when it comes to classical theory, right? So classical learning theory mostly didn't worry about the optimization error, and only in some very special cases can you talk about optimization error, right? So the trivial one is convex optimization. There's no optimization error. The one with linear algebra or tensor algebra, right? You can again talk about global optimality, but only under some limited conditions of perturbations, right? So and so in general, this is hard to evaluate, and that's why people mostly ignore this in theory and hope for the best. And we further discuss this decomposition into approximation and estimation error. You could also interpret in terms of breakdown into bias and variance, right? So in estimation, we mostly think of bias and variance. In learning theory, we think about approximation error and estimation error. and the two are not equivalent, right? So we saw components of approximation error contributed to both bias and variance, and same with the estimation error. So it's a different breakdown, and what we saw was one is like kind of different communities worrying about it, right? Like statisticians worry more about bias variance trade-off. Learning theorists worry more about approximation and estimation error. But if you further break it down, you can kind of look into the bias contribution from approximation, right? Variance contribution from approximation. So you can like break down each of these parts separately. And that's what we did in the previous class, where we said the approximation and estimation error contributes, right, both to bias and to variance. Right, so the variance, the part that is what I'm assigning to approximation error is really something inherent, right? It's not arising because of approximation. But when we talk about approximation error, we just include it, right? So that was the aleatoric uncertainty. And the epistemic one comes because there's only finite data, and that's contributed via the estimation error. So it's good to keep this in mind, how the different right formulations relate to one another. And the other main comment is, when we were talking about bias and variance, it's mostly in the context of square error, right? So mean square error, and then we were breaking down into the bias part and the variance part. So it's not that meaningful for any other loss function, right? So whereas approximation and estimation error could be for a general loss function. Although when you get into the actual bounds, the loss function does matter, right? And most of the bounds that we'll look at today for the estimation error, right, which is the generalization error, will depend on the fact that it's either a binary output, so meaning a binary classifier, and there have been extensions to multi-class. So it's limited to the discrete output. So that's why, the two are not kind of thought of in the same setup, because this is usually for classification, this is usually for regression, right? So that's the other reason why people don't, you may not come across both of them in the same paper. Although you can talk about approximation and estimation error even for a regression problem, right? And we did that in the linear regression case. But typically people don't, because all the generalization theory is looking at discrete outputs. It's the classification setting where this really comes up more. So that's the other reason why they're mostly separate. Right, but conceptually they're very related. Any questions here? So that's what we saw in the previous class, and then we started looking into approximation theory, right? So the idea is neural networks are universal approximators. So if you have an arbitrarily large neural network, even if it's just a single hidden layer, if you make that arbitrarily large, you can approximate any given function. You can fit any given function, right? That's why it's called a universal approximator. But on the other hand, if you limit to a finite size network, then you incur an approximation error, right? And if you want this to be a realistic network, right, we cannot make this arbitrarily large. We have finite computation limits, and that's why it's important to look at what are the approximation errors. And in the previous class, I gave the intuition that the approximation error will relate to the smoothness of the underlying oracle function. Right, so the intuition is if the underlying function is smooth, it's easy to approximate. But if it is a lot of high frequency components, right, then it is hard to approximate. And that's why we could directly relate it to the Fourier spectrum. So to recall, what we said was, the complexity constant, right, that determines the approximation error, you can relate it to the high frequency content of the function, and hence we can talk about it in terms of the Fourier representation. So let me just call this H oracle to be a function f. Just, I want to not keep writing it right throughout. And what we said was there is the Fourier transform of x, and this will be a function of frequency. So we are dealing with everything being continuous, right? X is continuous, omega is continuous. And if you recall the Fourier transform, right? This is how you compute it. And the intuition is, right, a smooth function has only low frequencies, right? It's slowly varying, and fast varying function has high frequencies. And that's why we said, if you look at the right, so sorry, this is the inverse, this is the Fourier, right? And what I want is the inverse Fourier spectrum. Let me use the notation used here to get the, so I want to represent my function in terms of, I guess this is usually j, and then there is the, right, so I want to represent my function in terms of its Fourier. Yeah, so that would be the inverse Fourier transform. I mean, there's also sometimes like a scaling, right? I'm ignoring the scaling here. So, right, so this was the Fourier transform, this is the inverse Fourier transform. So I'm representing my signal in terms of its Fourier transform. And now if I want to ask, what is the derivative of my function, right? So the idea is if the function is smooth, it won't have a large derivative, right? So the derivative, that's why is related to the high frequency content. And that you can see it directly here, because if you look at the derivative, right, you will have this term here, right, coming. So exactly, right, so j omega, right, sorry, it's just j omega e to the, yeah, I mean, this was the rule for the derivative, right? So if you had the rule here, you were looking at, right, omega times the Fourier transform, right? So this is the standard formula here, but the main idea is if you want the derivatives to be small, you shouldn't have high frequency content. And we said the constant we'll use is the magnitude of this, right? So I can bound this by looking at the magnitude here, and that's why that is just, right? So this goes away, right? J has magnitude 1, this is magnitude 1. So this gives me a bound on how smooth the function is, right? The smaller this is, the function is smooth. And we said the approximation error, right? So if I now have this function f of x, and I'm looking at its approximation using a shallow network, a one-layered network with k neurons, right? So this expected square error will be less than or equal to, and this expectation, if you do it only on a ball of size r, so you're only looking at x within some radius r, that is upper bounded by, it is r, I mean, yes, 2rcf squared. So the idea is, right, so ignore the r, that's just a bound, right? Obviously, if you have unbounded inputs, it's going to be a problem, right? You cannot approximate them well. So that's just to limit the bound on the input. And the other is this, right? This constant is the key, because what it says is it depends on what the function is, how smooth the function is. So the smoother the function, right, the better approximated it is with the network. And so this gives us an approximation error. And for different functions, you can easily come up with it. If it's Gaussian, we know we can compute this, right? So I think for Gaussian, it's root d, right? So in d dimensions for Gaussian, right, this bound is root d. So for a d-dimensional input, right? So if you have just a Gaussian input, so your function is Gaussian, this constant is root d, and hence the approximation error is d by k. Right, so if your approximation error should be small, you want k to be much larger than d. So the idea is you have like your dimension of your input increasing, you want to have a larger network, right? And this is very good, right, compared to an arbitrary function. Arbitrary function could have this, right, constant to be exponential in d, right? Whereas you take a special function like Gaussian, right, that's smooth, you have the constant being much nicer.
I might have missed, what is k then?
K is the number of neurons in the network. So we are approximating it. If you recall, right, this is what we had in the previous class. D is the input dimension, K is the middle layer, and the output right now is just binary classifier, right? The output is gonna be a scalar. And this is the approximation error. Any questions here?
Have people extended this to like stochastic gradient descent?
So remember, it's only talking about this.
Yeah.
So that's a completely different source of error,
Yeah.
right? I'll come to other aspects soon. But right now we're only looking at approximation. Yeah, we'll come to the other sources of error. And so one question, right, I guess a natural extension to ask is, what about multi-layer networks rather than one-layer network, right? What happens to approximation error? I mean, you can always, right, represent this multi-layer network with a bigger single-layer network, right? But that single-layer network requires an exponential number of units to represent, right, like many layers. So the exponential in the number of layers. Right, if you have L layers, your shallow network should be exponential in L, right, in terms of number of units to represent a deep network. So you can always reduce a deep network to a shallow network and talk about the approximation error for the shallow network, right? But the problem is, maybe the deep network has further structure. So in this equivalence, if you're going from, say, right, say I have many layer network, I can always map it to just one hidden layer, right? So this way I can always map. It's not both sided, it's only one sided, right? And I would have, of course, many units here. So if I have like L layers, this would be like exponential in L. Right? I can always represent it that way. Because all I need to do is, I need to look at the composition of all these units here, I put that here, right? But then, if I don't constrain any of the weights here, right, this has more flexibility than the network here, right? And that's why I can't just take an arbitrary shallow network and represent it as a deep network. because there are more constraints on the weights here. I'm reusing the weights because of compositionality. Do you see that? When I'm taking a deep network and representing it as a shallow network, the weights that I put in my first layer have special properties, right? There are not arbitrary weights. Because of compositionality, I've imposed certain dependency between them. And that's what people argue is a good inductive bias. We have, of course, even in our visual cortex, many layers, right, of processing, and many of the natural domains have compositionality. So that's why there is better expressivity in the deep network as opposed to shallow network for natural signals, right? For signals that have compositionality. And that's not captured just based on this approximation error. Do you see that? Because the approximation error, all it says is how smooth is the function, right? It doesn't say anything about how compositional is the function. If you have a function that is compositional in many layers, it's better to represent it as a deep network. And that's not captured by this theory.
For this approximation bound, upper bound, do we need to assume that one layer is fully connected?
Yeah, right now this is just arbitrary fully connected network, right? We are not, again, if it's convolutional, it wouldn't have the same approximation capability, right? Again, that's not being captured here. So, a convolutional network has more constraints, right? So it may not be able to, it won't be able to fit an arbitrary function. But on the other hand, we are not fitting arbitrary functions, right? In images, convolution is a natural inductive bias, and that's why it's okay to have it. Right? And that's why just this quantity does not say everything, right? So I'm talking about the limitations of this approximation error. Like all this tells you is, look at the smoothness of the function. If the function is smooth, you have low approximation error. And you can fit it to a fully connected shallow network. But it's hiding the fact that the function would have other properties than just smoothness, right? This is only capturing smoothness. And that the other property is inductive bias. If you know something more about the function, for instance, it's an image where there's translation invariance of your features, it is better to do convolution, right? And that's not captured in this BOM. And similarly, if your underlying function is compositional, there is some inherent compositionality of functions over functions. It's better to represent it with a deep network and not a shallow network. And that's what we see in practice, right? The practical gains that we see with many layer networks, it cannot be replicated with a shallow network, right? At least very easily, at least any large scale setup, you cannot replicate it. And the reason is, this theory does not capture that, right? If we have inherent compositionality in our underlying oracle function, it is better to use a deep network.
So for general continuous function, does deep network has any advantage over this?
No, there isn't. It's in fact kind of more constrained, right? So for a general function, it would be limiting.
But if I just constrain the number of parameters instead of the number of nodes, will that be more powerful?
No, right? Because you can always reduce it to a shallow network. As long as these two would have the same number of parameters, right? That's how I'm reducing it. But then the deep network would have more constraints on its weights compared to the shallow network, right? The shallow network would have more flexibility. So if your function doesn't have compositionality, right, you shouldn't be using a deep network.
So is there any difference on the optimization side? Deep network have?
Yeah, that's a different story, right? So again, the theory is very incomplete. People have argued, at least just with linear layers, recall if it's completely linear, you can always just, right, compress it into just one linear matrix multiplication, right? So you can always do that. But there people have shown if it's deep, there is acceleration in optimization. I mean, both cases, there's global optimality. So, it's a very different from the nonlinear setting, right? But that's, that's hard to analyze, but maybe there are some ideas for further research. I think I have some, insights that could be useful. But yeah, in general, no. The reason why we think in practice optimization is easier, right, in the deep network, we do see that, if you run any of the standard architectures, right, and try to run a shallow network and try to optimize it, it's extremely hard, right? And the reason is the deep network kind of is capturing the right inductive bias, and if you're capturing the right inductive bias, it also gets easier to optimize. That's the rough intuition. But again, trying to kind of show that in theory is much harder. Right, because inductive bias is a catch-all phrase for everything about the function, right? Here the nice thing is there's just like one constant, and you can use that for your approximation error. On the other hand, if you want to ask how compositional is your function, unless you assume a realizable setting where it is exactly compositional, you can't capture this very well, right? And that's the reason why there is this classical theory, and there's really not much of a theory I can write here, right? So that's why I'm only explaining the intuitions.
If the Fourier transformation of fx does not exist, so the bound will lose its power.
Yeah, so in this, at least there have been some, there has certainly been extensions of this bound, right? Because you can think in terms of wavelet transform, you can think in terms of multi-scale. But I don't think that has been fully translated into a neural network bounds. Yeah, so if this quantity blows up, right, this bound doesn't hold. And also that's because the proof technique, if you recall, we went first from sinusoids and then we kind of replaced them with sigmoids, right? So, but you can make extensions. So if this is, if there's some bounded smoothness in some other basis other than the Fourier basis, you can start with representation in that basis and then replace it. If it's not replaceable by sigmoid or relu, then it's a problem, right? Because the error doesn't carry through. And in a way, what this is saying is you already know in which basis, right, the representation is good. The Fourier basis is good in case of this constant, right, if this constant is small. So in a sense, you always have to assume something about the function, right? Otherwise, you cannot start. And that's also the reason why in practice maybe sigmoids are not that great, right? Because the images we see are not really smooth because they have edges. You really want to actually capture the edges in the image, right? Not the smooth regions. So that's within the image, but also I guess this is really, right, the classifier itself, it's not clear it is smooth, right? Because, maybe in some regions it is, but in others maybe there are big jumps. It's hard to say because we don't know what the true oracle function is anyway. Yeah, so that's also, there could be different reasons, right, why this theory is not appropriate or enough, but at least it's a beginning point. Any questions?
So, for deep network, because I have a lot of activation coupled to each other, it will be easier to approximate more deep functions than just a shallow.
Yes, that's what I mean by a compositional function, right? So that's the inductive bias. If I know my function actually has compositionality of many layers, it's better to use the deep network.
So can I say if my function is very deep, then I just need smaller parameters for my deep network compared to the shallow?
I mean, to me, it's more about the optimization then, right? Because in terms of representation power, you can always have a shallow network with the same representation power. But then, like in terms of optimization and in terms of number of samples, it's always better to go with a network that captures the inductive bias, right? So it's not about the approximation error, right? That phenomenon is more related to, right, the estimation and the algorithm. Because the rough idea is if you have better inductive bias, it's easier to optimize. You can do it with less number of samples. But it's not about approximation. Yeah.
Does the approximation error still come in though? Because I guess like depending on your activation, like for ReLU, like a two-layer network can define a function that you need an infinite number of nodes in a single-layer network too.
Right. I mean, there are always, as I said, there are functions, right, where this could blow up, right? And the question is, okay, how do you, then this is not a good bound, right? You could find other ways to bound it, maybe another basis instead of Fourier basis, right? And you can ask, can I now use them as activation functions, right? So, and then it will have finite approximation bounds there. Good. So yeah, so this compositionality is more about inductive bias, right? And inductive bias is not captured, right? Does not contribute to approximation error. So that's why don't confuse the two, right? This has nothing to do with approximation error. Good. It's all good with approximation error? So now let's go to the other part, right, the estimation error. Because as I said, this doesn't completely capture what we are observing in practice. So what aspects can we assign to the estimation error? And that's where, right, we'll have this notion of generalization. Because so far what we've been talking about is just fitting a function, right? There is now some function, I want to fit this to some finite sized neural network, how good is it, right? But if I have only finite number of samples, I don't want to completely fit to it, right? Because the idea is it should also generalize to new unseen samples. And that's why it's not just about the best function fitting, right? At least not so far. And that's what is the theory of generalization, right? The idea is, I'm trained just on my empirical loss function. How well does it generalize to my unseen test data? Right? So the intuition is, if you overfit to your training data, it may actually be bad, right? You won't be able to give good answers on your test data. And there is, there could be several reasons for overfitting, right? And that's what the generalization error tries to capture. How bad can it be, right? Is there a bound on how bad your generalization error can be? Right? And that's what, this is now the deviation from just like thinking about function fitting, right? Thinking about just optimization, global optimality, right? None of those capture the aspect of generalization. And that's why in a way machine learning is weird, because I give you a loss function, I tell you to optimize, but I don't really want you to do that, right? What I want is to be able to do well on new unseen data, but I haven't seen it yet, so I can't tell you what it is, right? And that's why it's so complicated. Right, and that's also the reason, right, like many optimization methods with better guarantees in theory may not work very well in machine learning applications, because somehow maybe the way they optimize leads to bad generalization errors, right, may lead to other aspects, but that could be one of the reasons. So we cannot just focus, right, just on the optimization error or just on the approximation error. right? This aspect of how bad is the estimation error is critical. And that's why there is a lot of generalization theory, right? And that's why it's such a big deal for neural networks. I'll come to it in a minute, why it's mysterious and harder to think when it comes to neural networks, especially the ones we see in practice today. But before I do that, let me set up a few things. As I said, the main idea behind generalization error is this notion of excess risk, right? Like I've trained and gotten my empirical risk minimizer, right? I've used my empirical loss to come up with this empirical risk minimizer. Now, how does it do in terms of the population loss, right? And how does it differ in terms of the loss compared to this best, this 8 star, right? The one that was optimized on population loss. So let me set up some notations here. If you recall, we had from the previous class, right? So we had H was a hypothesis, right? And so hypothesis is really a function mapping going from X to Y, right? From input to your output space. So you could call it a classifier because anyway, we only look at binary outputs in this case, -1 and +1 in this convention, in the theory I introduced now. So it's a binary classifier, right? So I know we used hypothesis when it came to detection theory, right? And now we're back to, it's the same notion, right? You have many different hypotheses, each one corresponds to a certain choice of classifier. And then, as I said, we have a loss function, right? So the loss function tells you how off are you, right? So there is a loss function that looks at, right, your true output, right? So for this, you have to have the label, right? So I look at the label, I look at what my classifier is telling me, and I put a loss value based on that. Right, the simplest one is 0-1 loss, right? If my classifier is giving the right answer, there is no loss, right? It's 0. And if it's giving the wrong answer, I put a penalty of 1, right? That's the 0-1 loss. But we could have other loss functions. So this is the loss per sample, right? But what I want is the expected loss, right, over IID samples, right? So mostly we limit to we will limit to IID setting, and that's the other reason why in practice the bounds may not work out, right? Because what we have in practice is far from IID due to so many reasons, right? So we are not just IID sampling from all possible natural images. Right? That's not how ImageNet was collected, or any data set for that matter is collected. That's not how internet is constructed. So, that's also a caveat, but the theory, mostly limits to IID setting. And in that case, we would have, right, the expectation over the true distribution, and I'm going to look at the loss, right? And this is the population loss for a certain classifier. So I pick a classifier, I look at what is its expected loss. This is the population level loss. I can do the same over my empirical distribution, and that's the empirical loss. I'll just use E hat, right? We were doing it also earlier in the class. And this is over training data, right? Because I only have my training data. And hence, now what I want is to look at, the empirical risk minimizer that I got, how different is it from the population level, right, the one that minimizes the loss. So we have 8 star is the one that minimizes, right, the population level loss. And the ERM, or I'll drop this notation again, I'll just call it H hat for the derivations we do now, just to keep it simple. So the excess risk is, how different is the loss that I obtain from my empirical risk minimizer compared to the best one. Right? This is called the excess risk. Because what I really want is the loss at the population level, right? But I don't have access to it, so I can't optimize for it. What I can do is, optimize on the empirical loss and hope for the best, right? And that's why this is our empirical risk, right? If you recall this is the loss function. This is really called the risk, right? From our basic classes. And that's why this is the excess risk. What is the excess I'm paying because I don't have access to my population loss function. I only have, or population risk, right? And I only have access to my empirical risk. And so this will then give us an idea how well it'll do on test data. Right, because if this is small, it will do well on test data. If this is large, it could potentially do badly on test data. Any questions here? So the question is now, how do we analyze this, right? How can we bound the excess risk? Right, so what are some intuitions here? What would the excess risk depend on, right? So what are some kind of high-level intuitions of when would excess risk be high, when would it be low? What do you think?
Are we assuming it's IID?
Yeah. When I wrote this expectation, it's, we'll do the bounds based on ID, although the expectation could have been for everything. But that's not so crucial, at least for high-level intuitions. What do you think?
Number of samples?
Sure, right? The number of samples should matter, and ideally, right, you want like fast decay with number of samples, right? Because, of course, if you have infinite number of samples, the excess risk will be 0, right? So that's a natural one. So let me call n to be the number of samples. We'll use this. What else would matter? When it came to approximation error, right, we looked at smoothness, but we could express the smoothness for functions in terms of dimensions, right, the input dimension. So this x, let's say, is RD, right? In general, what do you expect? As you increase the number of dimensions, right, in general, what should happen to excess risk? If you fix the same number of samples, it should increase, right? Unless there's something very special about the function. For a general function, you should have more error, right? And that's because it's harder to concentrate a higher dimensional function, right? Unless something magical happens or something special structure is there. So that's again another intuition, right? So it should depend on the number of samples, it should depend on dimension, right? But how precisely does it do that, and how can we kind of analyze this? So the first case, right, I will kind of quickly give the result. is this finite hypothesis class. So that wouldn't be a neural network, right? Finite hypothesis, if you recall, this is the detection problem we did, right? So it's only a finite number of hypotheses. So I'm giving you a bunch of classifiers, you can only choose among those, right? So there's no continuous optimization. You just kind of discretely choose one of the classifiers given. Of course, you wouldn't do this in practice for complex inputs, like rich inputs, but we'll just do it for the sake of how do the bounds look. And here, this is not so hard to see because we have one concept that is very useful, right? And that would be the union bound. Because all I need to argue is for each hypothesis, right, my empirical loss and my population loss is bounded, right, and I can do Hofting bound, right, or any, that's a concentration bound if you recall. And then all I need to do is do union bound over all the hypotheses, right? But before I get to that, I guess one point I forgot to mention that is, let me do it before I get to the finite class, is the notion of uniform convergence. So as you can see, this can be very complicated to analyze, right? Because this can be different based on what H star is, right? The optimal classifier based on the population risk, right? It depends, right, on, of course, the distribution and many things. So instead of that, we will kind of do a notion of uniform convergence, where you can argue that the excess risk can be bounded in terms of the worst case deviation between the empirical and the population risk over any hypothesis, right? So I'll upper bound the the excess risk based on this quantity. And this is called uniform convergence because now I demand that every hypothesis, right, in my class has bounded concentration, like concentrates, has bounded deviation. And to see that is kind of not too hard. You need to add and subtract a few terms. So we'll add and subtract the empirical loss we'll do the same. And also right here. So I'm adding and subtracting of two terms. And you can see that, from uniform convergence I can bound this. I can also bound this. What about this quantity? Right, there is this quantity that gets bounded from uniform convergence. This also gets bounded. What about this one?
Model equal to 0.
Why?
Because
you're minimizing this, right?
Ones should
yeah. So that's why, right? That's why uniform convergence gives you a bound on the excess risk. It's an upper bound, right? And it can be a bad upper bound, and that's what I'll come to when we talk about is this applicable for modern neural networks, but it is an upper bound. Okay, so all the theory kind of now only deals with, right, wanting to bound this. And that's what, sorry, I jumped ahead, and that's why for the finite hypothesis, this was now okay. Right, because I want to look at the worst case bound all I need is a concentration bound for each hypothesis, then I do the union bound, right? Then I get uniform convergence. So roughly what this says is for each hypothesis, right, we have, if you recall the Hufting bound, we have like L hat, this is the large deviation principle, right? So we have this being greater than epsilon is less than, I think, e to the minus n epsilon square. Is there a 2? I think there is a 2, but don't quote me on that. This is the Hufting bound, right? So for each hypothesis, and all I need to do is do a union bound, right? And what the union bound now gives me is, I guess I can also put this and put a 2 here. And then I can do soup, right? This is the quantity I wanted. So I'm just going to bound it by the number of hypotheses, right? This was just finite. So that's what union bound gives me, right? I just have to, multiply by the number of hypotheses. And so if the pack bound, what it says is, I want this quantity to be, like with high probability, right? So with probability, delta will have this quantity being be less than, it'll be like, there'll be log 1 over delta, and there'll be the number of hypotheses, right? And there's some constants I may have missed, but that's okay. Yeah, there was 2 here, 2. Yeah, it doesn't matter. Let's ignore those constants. Okay, there's 2 somewhere. Okay, if you want to be, sorry, the log also goes there, right? Sorry, this is first of all, of course, this is not true. We have the log here. I mean, that just comes from setting this to be equal to delta, right? So this is just algebra. I'm going to set that equal to delta, and then with probability, if I want this to be less, this is then probability 1 minus delta, right? Because with that much probability, it'll exceed. So this is now so there's no magic here. I just set that quantity here to delta, right? So nothing else. And so what are some things we can glean from this? So this is now telling me, right, with high probability, my excess risk will be bounded by this, right? And that's what we call, right, the notion of pack is probably approximately correct. That is pack. And so probably approximately correct means, with some probability, right? So in this case, the probability is 1 minus delta. With that probability, it's approximately correct, meaning it's, these are close, right? And they're close by this much. And that's called the pack bound if you haven't come across pack before. So what this is saying is this now, right, pack bound depends, of course, on the number of samples. Like your intuition said, right, it should decrease with the number of samples. It'll decrease as 1 over square root n. And that kind of makes sense, right? The variance is like 1 over n, right? And so its square root should be 1 over square root n. And in terms of like, if there are more hypotheses, right, that's like the dimensionality of our problem, right? So if you have more hypotheses, you should be having worse excess risk. But the nice thing is in the finite hypothesis case, it's only logarithmic, right? So it grows very slowly. Is it clear? Right, so this was the Hofting bound. I think we did this in the concentration bounds class. Right, Guanya, did we cover that? In probability class
No,
you did?
Sorry, you mean Hofting?
Yeah.
We didn't do Hofting.
Okay,
Yeah.
but it's similar to the other bounds that Guanya did, right?
We did Rademacher, Chebyshev,
Yeah.
Chernoff.
Yeah. Right, so I mean, this is like kind of average of quantities and its expectation, right? So you're looking at the deviation from expectation, and then simply it's the union bound, right? And then we get the back bound from that. Any questions here? It's all good? Right, so I won't do the derivations for infinite hypothesis, but now I'll give some intuitions, right? Because the main idea is now if I go from finite hypothesis to infinite, I can't just do union bound, right? This blows up. I mean, I cannot just count the number of hypotheses. So I can't count all the classifiers that some neural network will give me, right? That's infinite because they're continuous parameters. So I cannot bound complexity through this simple union bound. So how do we bound the complexity? And that's where we'll use the notion of Rademacher complexity. I'll not go through the derivation, but I'll give some intuitions of what it is. But any questions here?
The lacquer of the inequality should be the population loss between global minimizer and
Recall this was the uniform convergence, right? So this implies excess risk is also bounded. That's because of this inequality. I mean twice, right?
Twice.
But yeah. That's why we're just bounding this. This implies excess risk is also bounded, right, by twice that amount. Any questions here?
So it's just, so for H is like, the size of it is the size of our hypothesis set.
This is finite, right? It's just a finite number of hypotheses. So think I'm giving you only finite number of classifiers.
Okay.
That's why it's a special case. This is not we'll do in practice, right, with neural networks.
Yeah, the classifier parameterized by like one parameter is like as if it only had that parameter itself.
No, but even if it's continuous, it's infinite, right? Only discrete parameters.
Yeah, so if it only had like 5 discrete possibilities.
Right. Or you can like kind of take some fixed weight classifiers, right? Few of those, and then you can say what is the complexity for that class, or excess risk bound for that class. And that's why this is more a toy setting, but it gives again the, first of all, the fact that it should be 1 over square root n, I think shows up, right? So this should extend because, this between the empirical and the population risk, right? We expect it to be 1 over square root n. Right, and then the true question is, now what do I replace this number of hypotheses with? Right, how else do I measure my complexity for infinite hypothesis setting? I can't do the union bound. And that's where there is a notion of Rademacher complexity. And that's only for this binary hypothesis, right? And it's for this plus minus one convention. So keep this in mind, right? Because what I write now, it's specific to that. So far it hasn't been, right? This is true even more generally. I guess except, instead of Hopting bound, you want to use your favorite concentration bound there. So the notion of Rademacher complexity again, like at this point, right, what we want is some upper bound in terms of, right, like what is the capacity of this function class, right? So the idea is if this function class has large capacity, meaning it can represent a wide range of functions, it should have higher complexity, right? And in simple finite case, all I did was count. But instead of this, I want to like now have a way to think about the capacity of my function class. And in the context of neural network, it would be the size of the network, for instance. Right? If I had a bigger size, it has more flexibility, and hence there is a larger set of hypotheses that are possible, right, to be represented by that function class. And that's the notion, right? So if it's a larger now neural network, it should have higher complexity than a smaller one, because it has more capability to express a wide range of functions. And because we are looking at this uniform convergence, there could end up being one function that's bad, right, or one hypothesis that is bad, and then you're bad, you're done, right, because the bound depends on that. And that's also the limitation of like this analysis, right, because it says, if I now have a very flexible function class, so I have a large neural network, I can represent all kinds of functions with it. If there is one function where this is bad, right, that determines my bound on the excess risk. And that's why, right, that's only an upper bound. On the other hand, you may not end up ever representing that function or learning it from data, right? So it shouldn't matter. But this bound does not capture that. It just looks at the worst case, because it looks at all possible functions that can be represented by that neural network, and looks, in the worst case, how bad is this deviation. Okay, so that's the intuition of like Rademacher complexity, VC bounds, all these things we'll look at, right? It's the idea of, right, what is the capacity in this function class or hypothesis class. So I'm using function and hypothesis in an interchangeable way, right? Is that intuition clear? So now to actually define this Rademacher complexity, it's, you randomly draw plus and minus one and essentially randomize your function. Let me look at the exact expression. Right. So what we'll do is, look at the, if you recall, for each sample, I can look at my loss function. But what I'll do is now I'll take an independent random variable, a Rademacher random variable, right? Multiply with this, take the average, of course, and take the expectation. There's soup and then there is the expectation. This is the definition of Rademacher complexity. So the Rademacher variable is one where you draw plus and minus one with equal probability. That's a Rademacher variable. So intuitively what this is saying is, right, like what is the capability of the network to fit to just random labels, right? So if you had like one of the functions being just generating random labels, right? Because this is what kind of the output is now just random labels, right? Because I'm just drawing this independent of anything to do with the input function, with x or y. And so this is a symmetrization trick. I won't go into the details of the derivation, but what this gives me in terms of the uniform convergence is, so I'll just go to the excess risk bound, because now it's twice of that. It's just twice this Rademacher complexity, and there's one more term. I mean, this is just like another 1 over root n term. So I didn't go into the, of course, this is less. So the idea is I can bound the excess risk in terms of this Rademacher complexity. And you can think of it intuitively as what is the capacity of this network to fit to just random labels, right? So random labels that have nothing to do with the input. Of course, that is, in practice, you would never end up with random labels, right? That wouldn't be an interesting machine learning problem. But all I care about is uniform convergence, right? I'm looking in the worst case, what can I think of as a bad hypothesis, right? So bad setting is if you're trying to fit to random labels that have nothing to do with input. And intuitively, that's why that gives an upper bound. Okay, I skipped the details, but I hope you got the intuition from it.
This bound lower than the...
This is different, right? This is finite hypothesis, that's now infinite hypothesis. So it's extension of this bound to infinite classes. Right? So instead of this log of the number of hypotheses, I have this Rademacher complexity. And there's also one more additive term. But typically this will be the dominating term, right? Because now this will incorporate the dimension. So I still didn't mention what will this term be for different classes of functions. For neural network, what is R? I have to characterize now. So ignore this term, this will be lower order compared to this one. So we'll just look at some special classes, because I don't want to kind of, I think in the remaining time, I want to focus more on intuitions. So just quickly, giving some bounds on the Rademacher complexity for some special classes of functions. So I can look at my linear classifier, right? So if it's a linear class, all I'm doing is looking at, right, a linear transformation, and then maybe I'll do like sign, because remember this is just binary classifier, right? So this is my linear class, and for this one, the Rademacher complexity is root of t by n log. And that's the intuition, right? So we had the saying that as the dimensions grow, you should have higher complexity. And the intuition is, as the dimension grow, your weight vector, this is binary, so it's only a vector, right? So it's d dimensions, so you should have the capability to represent more functions with a larger d, right? It's still a simple linear classifier, but then its complexity is growing as d grows. And that's why this is, the bound. If it is, on the other hand, bounded, right? So this d is just the ambient dimension, and we had no constraints on what the linear classifier can be, right? It can be any arbitrary weight here. On the other hand, if the weight has, say, some norm bound, say this norm is some beta, you can replace D with beta instead. Right, so essentially, if you know something more about your function class, you can reduce the complexity. And that's the notion of regularization, right? So if you do, now this is L2 regular or any other, right? Like in this case, I think this was L2, but you could do different kinds of regularization and that will bring down the complexity, and hence it'll give you better generalization. And the intuition is, right, because now you're limiting the complexity of the function class, right? Essentially the number of possible functions you can represent is more limited because of regularization. Is that clear? And so for neural networks, a simple way to extend this from the linear bound is to do it multiplicative. So in each layer I have a bound because, right, it's a linear classifier, and then I have some non-linearity. So I can just compose the bound many times, and that's what is a bound for the neural network. It's here again, of course, you have square root n here. If you assume the input has, say, bound, you have all bounded inputs, right? That bound will also come up here naturally, right? The bound on input should be there. If you have bounds on your first layer weight matrix, let's say this is B1, that shows up here. So this is a spectral norm bound, right? Because it's on the matrix now. And then the second layer is just a vector because it's just a binary classifier. Let's say this is B2. I have this one. So I'm essentially kind of composing, right, many layers and using this result. So sorry, the beta should be outside, right? So if I have this, it should be beta, because if it's unconstrained, it would be, the norm should be like order square root D. And so essentially, right, this would have been one layer. I mean, the log terms I'm ignoring, right? There's also the log terms, I'm ignoring those. So, right, so that would be the first layer. The second layer, I can just compose them, right? So,
do they take care of the activation function?
yeah, so you can assume like activation function is bounded, right? Like sigmoid, or even ReLU is fine, like, So composing from different layers.
We'll multiply the molar capacity layer.
And that's why it's the worst case, right? So it could be in practice better than this. And if you have further bounds on your weights, right, that is much nicer. Otherwise you will just have the, it will be the square root of the number of parameters in that layer, right? But it could be better if you do regularization. That's why regularized networks would have better generalization bounds.
So for D and like beta, in this case, if you have both, do you take the minimum? Like,
D and one.
D and like, let's say,
what is the other one? Beta, okay.
And yeah, D is like, I thought that was the output dimension.
The input. The output dimension is just binary.
Oh, right, sorry, input dimension. I guess, intuitively, why is that interchangeable with like the norm of the weights?
It gets better, right? So the idea is, if you don't put any constraints on the norm of the weights, you pay the price in terms of ambient dimension or the input dimension. But if beta is smaller, right, so beta has some like small value, then you can get a better bound, a tighter bound.
Yeah, I guess for me it's like, let's say your dimension, if the dimension is 10, it doesn't directly translate to me why, let's say, if our beta is 9, then...
Oh, this only matters in high dimensions, right? So think of the regime where D is very large, and then you're making beta small. right? Only then this is meaningful. Which is what we would see in practice, right? You have high-dimensional input. You want to regularize your network and limit the complexity of the class. Otherwise, there's no need to regularize, right? So what this says here is, right, this bound. So if you just look at this bound, it says your number of samples should be much larger than your dimension. Otherwise, this bound just blows up. So this is called the under constraint setting. Under parameterized, sorry. What's that? Under. So there are fewer parameters than the number of samples, right? The opposite is the over-parameterized setting. So what this bound says is your generalization error is small only in the under-parameterized setting, right? It is a cardinal sin to have the dimension of your model be larger than the dimension of your, than the number of samples. Right? But then that's where the modern theory, tries to also look at the over-parameterized case. I'll come to that in a minute, but I hope you see this, in terms of classical theory, you should always go for under-parameterization, right? So there's different ways to talk about complexity, right? Either in terms of the input dimension, in terms of like norms, right? If you have further regularizations, you can bring down that complexity. But you always want to ensure your number of samples is bigger than whatever this term in the numerator is. Right? In this case, you want your number of samples to be bigger compared to these terms in the numerator. Right? Or like another way to see this is if you have a fixed number of samples, you want to regularize your network in such a way such that this bound becomes small, right? The numerator becomes much smaller than the denominator. But then in practice, it doesn't regularizing may not always work out, right? So sometimes it tends to get over-regularized and you don't get good results. Because if you over-regularize, you could pay the price in approximation error. Right? That's the delicate balance, right? So you put very strong regularization here, your approximation error becomes large. And that's why you may see like your training loss not going to zero, right? In kind of the neural network settings. And that's why it's a delicate balance. Right, so it's this balance between how much do I regularize the network and what is the resulting generalization error I pay. So to make the generalization error small, I want to regularize it as much as possible. But then I pay a price with approximation error. Right, so that's why it's a balance between the two. Any questions here? Yeah, so far so good, right? So, but unfortunately, for the modern neural networks in the regimes we operate, this really doesn't explain what's going on. So that's why there's been a lot of interest in the last few years to ask, what are we missing here? What are we missing in this picture, right? So to me, I think the primary thing we are missing is by looking at uniform convergence, right? So if I'm only looking at this concentration over all possible hypotheses, right? Which means it's all possible functions a given neural network can represent. There'll be some bad function. Right? But then I don't care about that bad function. What I really care about is how well does it fit my underlying function of interest. Right? And if that's a good function, then I'm okay, right? But this uniform convergence means I cannot characterize that well. So think of like a setting where, say, right? So this is my training data. Let's just say this is my just 4 points, right? I could have a function that goes like this, right? This could be my underlying function, or this could be my underlying function, right? Like both are valid, right? Because both explain my training data. So the idea is if I have now a very high capacity network, a network with lots of neurons, I can represent even this bad function, right? And that has a bad deviation bound. And hence my generalization error according to this Rademacher complexity is bad. But on the other hand, if my underlying function is truly smooth, doesn't matter, right? Because I'm never going to consider that function. Like as long as during your optimization you don't encounter that function, it's okay, right? So it also matters what's the optimizer you're using. As long as you don't get to this function, like throughout you optimize and you get to only the smooth function, you don't pay the price in terms of the uniform convergence bound. And that's, I think, a primary limitation with this classical theory. Any questions here? Right? And that's what, right, like you may have heard of this double descent curve, right? That's what that kind of like says. So what is the classical theory saying? The classical theory of overfitting says, right, so I have this model complexity, and I have my, let's say, test error, right? And so the classical theory says it's a U-curve. Right, so there's some optimal answer for what is the best model complexity. If I make my model complexity too small, so I take a tiny neural network, I pay the price with approximation error, right? Hence my test error will suffer. If I make my network too large, I'll overfit. I pay the price in terms of Rademacher complexity. And hence, again, my test error could suffer. Again, these are upper bounds, right? That's why this is a theory. And hence, I should choose my model complexity based on my validation set, right? So you have this validation set, you try to kind of search what is the best parameter, what's the best size neural network, or best regularizer, right? So you search and you find the best, right? This is what the classical theory says. But what the modern theory says is this is not the complete picture, right? This is only true up to the limit of over-parameterization. So this is all like in the regime where your model complexity here, right? However you measure it, because there are different ways to measure, right? But in some ways to measure in terms of the order, right? Here this is now far smaller than n, the number of samples. But if you go to the over-parameterized regime, it turns out it can further keep decreasing. And so this is the over-parameterized regime. Right? And the argument is most of the modern neural networks operate in the over-parameterized regime. Right? Again, it depends on how you measure complexity. I wouldn't completely buy the argument in every case, but the idea is we are certainly operating in higher parameterizations than what we've seen with classical machine learning. Right? So, and there's kind of this argument of a phase transition where, as soon as I have this over-parameterization, the classical theory no longer applies. And what instead applies is interpolation. And so to me, I think the main kind of reasoning is what I put there, right? If I'm looking in the lens of interpolation rather than in terms of the complexity of the function class for uniform convergence, right, the picture changes. Because when it's interpolation, I'm not going to worry about this, right, this bad function. You know, for uniform convergence, I need to bound for both of this. But for interpolation, I only need to think about how well can I interpolate based on my training samples. So if I have these, again, as my training samples, so in the over-parameterized regime, I'm going to be perfectly interpolating, meaning I have zero training loss, right? So I perfectly fitted my function to my sample points. According to classical theory, this is bad because this could overfit, right? And indeed, there is a bad way to overfit, right? If I interpolate but have these big jumps between the interpolating points, you know, I can come up with really bad answers on my test data. But the intuition is when I'm doing stochastic gradient descent or similar local algorithms, right, there's also implicit regularization. So I'm not going to end up with a function like this, right? So there is implicitly, it's regularized. It's more encouraged to be smooth like this rather than with a lot of, right, non-smoothness. And that's why, right, it's okay. Like what's happening in practice is okay, right? It doesn't violate the theory, it's just the theory is too loose the classical theory is too loose to explain what's going on in practice. And there is the interpolation bound. So this is, in interpolation theory, this in fact has nothing to do with machine learning, where what that interpolation theory says, and that's only for deterministic functions, but the main result is exactly this intuition, right? You have good interpolation for smooth functions. So if your interpolator is also smooth, your original function is smooth, then you have good approximation even everywhere else, right? So the idea is so there is now some, right, this is my underlying function. So wasn't the head star there? This is more the oracle, right? Maybe I'll use, this is the oracle. And then this is what I'm coming up with, right? Say this is my empirical classifier based on my empirical risk, and or anything, right? So I'm not based on minimizing empirical risk anymore. Just the fact, so the two quantities that matter here, you know, there's some norm, right? I can choose any norm. I'm not. So the two norms that matter are just the norms of what is the smoothness of my underlying function, as well as the function I'm interpolating it with. If both are smooth, I have good approximation. And the kind of argument is, you know, if you look at this regime, right, this is the interpolating regime, this bound matters more than and the uniform convergence bound is too loose to explain what's happening.